Right. Good afternoon. Welcome back. I'm delighted to introduce Virginia, who will start our fourth tutorial series, and this time it's on fine-grained complexity. These are the things I learned a lot when trying to optimize queries in an optimizer. So personally, I'm very excited to get this started. Please take it away.
Thank you. Let me know if you can't hear me. I can talk louder. Okay, so some of you have seen some versions of this talk. Hopefully, maybe it's a little different from usual, but for many of you, you may have not seen it, so I'm really excited to share this stuff with you. Okay, so this is one of 4 lectures that we'll give, me and my student Yunjun, who's over there, and my former student Nicole, who will be a professor at Michigan soon. Okay, so I will start. What is the main goal of algorithms research? We have a bunch of fundamental problems. We want to find the best algorithm for them. And usually this is in the worst case. And what best means is usually the fastest running time. What is the fastest running time? Let's say your input size is n. Typically, you have to read the input. So the best we typically want to get is linear time. And the good news is for many, many problems, we've gotten there. We have, even this year, we've gotten new and new algorithms for all sorts of problems. We keep getting close to linear. And we have a lot of these techniques, and we keep combining them, inventing new ways to do things, and adding more and more things to this box. Yet, unfortunately, there's a lot of problems for which we're still stuck on. And this comes to a very old quote from Gödel, who was thinking about exhaustive search. For all the problems we work on, they're usually in NP. And if they're in NP, there is some algorithm to solve them. There's some exhaustive search algorithm that's defined by the verifier of the NP problem. And the question is, can we actually do better than this exhaustive search algorithm? And often, we just don't know if you can do better. And this is extremely frustrating if you work on algorithms, because you really want to get something, and yet the stupidest solution you come up with, you can't even beat that. What are the type of problems that we get stuck on with our techniques? Well, they're all over the place, from very diverse areas, some from databases, some in logic. Very important, you have to solve them in practice. Often you look at this problem and you say, you know what, I'm just going to throw dynamic programming on it. Okay, it works. But then when you analyze the running time, it's something bad. It's cubic or quintic or quadratic, right? And sometimes it's 2 to the n. Often this is extremely slow, and in practice you would never run such an algorithm, even though you can immediately come up with it. And you go in the literature and you see a lot of people have tried to solve these problems forever and ever, and they all came up with the same algorithm you did, and nobody did better, and we don't know why. Here's a canonical example. So we all know the K-SAT problem. You have n Boolean variables and a bunch of clauses, so it's in conjunctive normal form. M clauses, all of them are ors of literals, and you want to know, is there Boolean assignment to the variable? So for every clause, at least one of the literals is set to true. And of course, because it's a problem in NP, there's a brute force exhaustive search algorithm, which is try all possible assignments to the variables and plug them in, and there you go. When you try all possible solutions, you know whether there is a satisfying assignment or not. And this running time would be 2 to the n, the number of Boolean assignments to the variables, times the time to plug in, which is usually linear time and the size of the formula. What is the best known algorithm? For every width of a clause, k is the maximum number of literals per clause k, there is an algorithm that runs in 2 to the n minus some constant times n divided by k. And people improve on this constant, and as a polynomial in the number of clauses. But unfortunately, this over here disappears as k grows. So as the size of the clauses grows, this running time goes to 2 to the n, which we could have gotten just by doing exhaustive search. Which is, again, one of these frustrating things. And to repeat, we don't have a 2 to the n to the 1 minus epsilon time algorithm where epsilon works for all k. So this algorithm works for all k. It's the same epsilon. And it's an embarrassing open problem to do that. Here's another hard problem. Okay, we know KSAT is hard because it's NP hard, but this problem is not NP hard. What is this problem? You're given two strings and n letters over some alphabet, let's say A, C, T, G, and I want to know if the largest length of a sequence that appears in both of them. So a sequence is not it's a string, but they don't have to be consecutive letters, so you can skip. Okay. So for example, for these two, the blue letters form a sequence that appears in both, and it happens to be the longest. It's an alignment problem, so you can think of as aligning the letters of the maximum length sequence, and then there's some things that don't match. And you want to maximize the matching letters in the alignment. You can put gaps here to skip some letters. So this has a lot of applications and spell checkers and computational biology where you might have like DNA sequences, you want to know how similar they are, all sorts of applications of where you want to compute similarity of sequences. And what do? You use dynamic programming, and we teach it in our algorithms courses. You can use dynamic programming to solve this problem in quadratic time in the number of letters in the sequences, so n squared. The best known algorithm is from the 80s by Masek and Patterson, and it runs in n squared divided by log n squared. So you can do a little better than n squared, but it's not much better. There is no n squared to the 1 minus epsilon time algorithm for this problem. Okay, so this is kind of similar to SAT in the sense that there's some easy algorithm that runs in t to the n time, yet we can't get to t of n to the 1 minus epsilon time for whatever reason. There's some seeming barrier for our techniques. Here's a problem from databases. Okay, so here you have a database which is from the strings of length n, binary strings, and your queries are. So this is D actually. Anyway, D. So this the dimension is D. So now you want to you have n queries, and each query is also a string of length D. But the string can have a star, so 0, 1, a star. And what you want to know for every query, is there something in the database that matches this? What is a match? If in the query in the ith position you have a star, star matches both 0 and 1. If it's a 1, you have the string in the database also have to have a 1 there. And if it's a 0, it also has to have a 0. For example, over here, 0, 1, 1, 0, 1 matches this string here with the stars. So the star matches everything, 0 matches with 0, and 1 matches with star. So we want in the batch partial match problem, we want to know for every query, is there some match in the database for it? Okay. How fast can you solve it? Well, there's two very simple algorithms. The first one is, well, for every query and everything in the database, check if they match. That runs in n squared times d times. So the size of the database is n, the dimension is d. For every pair, the number of pairs is n squared. D is the length of the sequence. Again, sorry about the typo here. And so n squared times d is very easy, is the brute force solution. You can also pre-process all possible queries in advance. And because the dimension is d, there's 2 to the d queries roughly. And then you can check. Whenever you get a query, you check whether what you've pre-processed works. So there's actually a better algorithm. If your dimension is c times log n, then you could get n to the 2 minus 1 over order log c. But if c is a constant, this is less than quadratic. But if c is not less than a constant, then this is not subquadratic. So again, we have this issue that there's no n to the 2 minus epsilon time algorithm known for this problem, even though n squared times d is very easy and d is very tiny in our case. So to recap, there's many of these problems. there you can usually come up with a simple algorithm, analyze it, and you get some running time t of n. But we don't have a t of n to the 1 minus epsilon time algorithm for any of them. And the question for me that's interesting to me is, are those problems secretly the same one? So could it be that the reason that we're stuck on all of them, even though they have different running times, maybe it's the same, okay? And then, maybe one of you will spend a lot of hours and figure out one algorithm, and that algorithm will solve all our problems. This is what we want. Why are we stuck? Are we stuck for the same reason? So this is what we want to achieve. So what I'm going to do now is I'm going to tell you just a little bit about some traditional hardness and complexity and why it doesn't quite work for us. And then we'll discuss the fine-grained approach, and then I'll give you one example of a reduction. Let's try to do this first. Okay, so when we teach complexity courses or take complexity courses, we see theorems of this nature. This is a very simple example. For every integer c, there's some problem solvable in n to the c time, but not in n to the c minus epsilon time. And this is just an example for polynomial time, but there's much more general theorems than this. So there exist problems for which you can get some running time, but improving on this running time substantially would be impossible. Now, of course, we don't care about the existence of problems. We care about longest common subsequence or SAT or batch partial match, which are not these problems, which are very contrived in a sense. So we don't know how to show that our favorite problem is not in this much time. For example, we don't even know how to show that SAT is not in linear time. Well, maybe SAT is in linear time, but I don't know. All right. So here's another approach from complexity theory, P versus NP. We believe, for whatever reason, P is not equal to NP, and it's a notoriously hard problem. This is roughly what P and NP are. You all know that. So we have this beautiful theorem that says that K-SAT is NP hard for all K at least 3. And what it says is that if we really believe that P is not equal to NP, then K-SAT doesn't have a polynomial time algorithm. Okay? In other words, making some hypothesis, P not equal to NP, we can derive a lower bound for SAT. It requires super polynomial time. All right, wonderful. We have conditional hardness. Now, we made up a condition, for whatever reason we believe it, and now we immediately get hardness for SAT. Okay, so, but does this help us? No, because a problem that's already in polynomial time cannot be NP hard. Okay, so problems like longest common subsequence, batch partial match, we cannot prove hardness for them in this way. So we got to do something else. So how do we prove NP hardness? We assume P not equal to NP, then we show that if some problem Q had a polynomial time algorithm, then you can solve every problem in NP in polynomial time, and therefore we conclude that Q requires super polynomial time. This is via some reduction. All right? And as I said, no problem that can already be solved in polynomial time can be NP hard, because if we show NP hardness, then you would immediately get P equals NP. So there's no way to use this for our purposes. And instead, we have to do something else. And in other words, NP hardness is too coarse-grained because it doesn't care about the running times in particular, and it's not useful to us. All right, so I usually have to take an aside and talk about why we as a computer scientist say that polynomial time is efficient. Okay, nobody in practice says polynomial time is efficient because it's not. So n to the 10 is not, n squared is not, and so on, right? Because really, why do we care about that? So we care about polynomial time being efficient because, well, we can completely disregard what model of computation we use. Whether you're working on a Turing machine, on a RAM, or whatever, your favorite pointer machine or whatever, you can translate between these machine models at a small polynomial overhead. So if you have an efficient algorithm on one model, then it's also efficient in the other model, whenever polynomial time means efficient. So it allows us to have this freedom in theory to forget about the machine model. And it also has this thing that polynomial of a polynomial is a polynomial, which is extremely useful when you use a polynomial time algorithm within a polynomial time algorithm. It stays polynomial. So if you forget about polynomial meaning efficient, you have to be more careful how you compose things. But in any case, so what we're going to do is we're going to take the idea from NP hardness, this conditional sort of hardness, and fix it so that it now cares about concrete running times. It won't be only about polynomial, it will be about quadratic, cubic, 2 to the n, 2 to the squared of n, whatever running time we pick, and we'll be careful about it. Okay? So this finishes this part of the introduction. Are there any questions at this point? All right, what is the fine-grained approach? So what we're going to do is we're going to take NP hardness. It is a very silly way to look at it, and we're going to convert it into something a little bit better suited for our purposes. So here we made this assumption that P is not equal to NP. For fine-grained hardness, we're going to make different assumptions. We're going to pick some problem, H, for example, SAT, and a running time, H of n, for that problem. And we're going to assert that H requires H of n time. Maybe you save some polylogs here, but you cannot do better than that. So you require H of n to the 1 minus little o of 1 time on inputs of size n, and you fix your computational model, for example, the RAM. Or you could pick a different computational model here. So you fix your computational model, pick a problem you really believe is hard for whatever reason, for this running time. So this is the type of hardness assumptions we'll take. Instead of SAT requires super polynomial time, which is the same as P not equal to P. The reduction, so what the reductions over here implied that if a problem Q has a polynomial time algorithm, then you could use that algorithm to solve SAT in polynomial time. This is a very rough consequence of the polynomial time reductions. And what our reductions will have as a consequence is that if a problem Q can be solved faster than Q to the n time, Q of n to the 1 minus epsilon time, for its running time Q, then you could use that algorithm on the RAM to show that problem H also has an improved algorithm, but for its running time. So this is not the definition of a reduction, it's the consequence that will derive from the definition of the reduction.
So what's the exact relation between epsilon and delta? There for any epsilon, there is a delta? Or?
Yes. So, all right. So for every epsilon, there is a delta. That's right. And I will have a formal definition in a little bit. And epsilon and delta can be very different. It could be the same. One could be bigger. You know. And after this, from this consequence, similarly to here, we'll conclude that if you believe this hypothesis, then Q must require this much time. So the hypothesis will be about a problem with this running time, and the conclusion will be about a different running time, a different problem. Okay, so what I'm going to do, oh yeah.
So the basis for choosing H is being there for a long time.
Great question. Yeah, see, he's asking how do you pick H? So I'll get to that. You have to be very careful how to pick H, because maybe Ryan will spend most of the night and resolve H, and then you gotta be careful. All right, so here's one H, okay? People have worked on SAT for many, many decades, and this hypothesis actually has appeared in the past. So in Pagliazzo and Paturi, and then Calabro and Pagliazzo Paturi, it was given here as a hypothesis, and it was named over here. So the hypothesis is that for every epsilon, there's some clause with k, so the k SAT on n variables m clauses can be solved in 2 to the n minus to the 1 minus epsilon time, basically. So for every epsilon, I can give you a width k for which you cannot solve k SAT in this running. So basically, k SAT as k grows requires 2 to the n time. So this is one hypothesis you might pick Who knows whether we believe it? Some people believe it, some people don't. But the point is we don't know how to prove or disprove it. And maybe it's true. So we can use Seth. But there's other hypotheses we can make. Oh, notably, this is much, much stronger than P not equal NP. Not only is Seth not in polynomial time, but you can't even beat the brute force algorithm. Maybe it's true. So there's 3 other problems from different communities that we often prove like results from in fine-grained complexity. So I'm going to define them on the next slide. So in all of these problems, we will assume the random access machine model with order log n bit words, where n is the size of the input. And the 3 problems are the 3 sum problem from computational geometry, the all pair shortest path problem from graph algorithms, and orthogonal vectors, which appears in many places. Also, it's equivalent to one of the problems I mentioned earlier. Okay, 3 sum. You have a set of n numbers. Let's say they're integers, and I want to know if 3 of those integers sum to 0. Okay, it's very easy to solve in n squared time. We give it as a homework problem in algorithms. With hash tables, it's super easy. You throw the integers in a hash table. You compute every pair a plus b and check whether the negation is in the hash table. So with hash tables, you can do it. There's also a deterministic quadratic time algorithm that does some sorting and uses pointers.
I have a question.
Yeah.
So what's the size of the input exactly in this case?
Okay. Assume that the integers fit in a word. So they're order log n bit integers, and there's n numbers. So the size of the input is n log n, order n log n. And in the word RAM model, you can do word operations in constant time, so n squared is.
Maybe he's asking about over the real.
Over the reals is in the real RAM model. Yeah, this one is for integers, so I didn't get here yet, but yes. So Brandemain and Petrashko in 2005 showed that if your numbers are actually integers, you can shave a log n squared off of the n squared running time. And Chan showed that for real numbers, now in the real RAM model, we have to change it, you can get the same. And the hypothesis is about the word RAM model and order log n bit integer inputs. It is the 3 sum requires quadratic time, n to the 2 minus little o 1 time. So you cannot get n to the 1.99999 time. If you don't believe it, please disprove it. I want to see the new technique. It will be great. All right, the other problem, very simple also. So you have n vectors, and they're very short. So they're over, let's say, log squared n dimensions. Very small. And they're binary, 0, 1 vectors. And I want to know if there's a pair of these vectors that are orthogonal. Okay. Is there a pair that's orthogonal? How can you solve it? You try every pair of vectors and compute the inner product, and you check. Is any one of the inner product 0? That's n squared times d. The best running time, Ryan is one of the authors there. So they showed that basically if d is some constant times log n, you can get a subquadratic time algorithm. Now this factor here is no longer a constant when d is more than log n, like log n squared, log n times log n. But this is the best known algorithm right now. And there's a hypothesis that in this word RAM model, orthogonal vectors requires quadratic time. You can't improve over this running time. Why should you believe it? Well, there's reasons. So I'll tell you about these reasons in a second. So the third problem is from graph algorithms, all pair shortest paths. You have an n-node directed or undirected graph. It has some weights. Let's say they're positive integers. Doesn't actually matter too much. You want to compute the distance between every pair of nodes. There's many ways to solve it. You can run Floyd-Warshau. You can run Bellman-Ford from every node, whatever, many algorithms. And the classical algorithms run in cubic time And Ryan, again, see, he's been trying to disprove them. That's why I made a joke earlier about. So he also has the best running time for all pair shortest paths. It runs in n cubed over an exponential of square root log n. So if the square root weren't there, then we would have a subcubic time algorithm, but the square root is there, unfortunately, so it's still basically cubic, the best running. So the hypothesis from graph algorithms is that we cannot beat n cubed time substantially by more than an n to the little of one factor.
Do you know if the distance, so the weights make a big difference here? So what if you just need to answer 0 or 1 for every pair of nodes, if there is a path or not?
If there is a path, then it's easy. So then if there is a path, then that's a transitive closure problem. It can be solved with matrix multiplication.
All pairs, the all pairs version as well. Yeah.
All pairs version, also if the weights are small, you can do better than cubic. So the weights really matter. Yeah. So in fact, there's a kind of a threshold. The moment the weights become roughly, in terms of roughly n, that's where we can no longer do better than cubic. So, yeah.
Why isn't this problem a matrix multiplication problem? I don't see
this one is a matrix multiplication problem over the tropical semi-ring. So that's what it is.
It's because
but the problem is we can't do
so you
that.
can't choose the.
Yeah, so min plus. It's min plus, it's not our favorite. Okay. So, all right, so now let's go back here with orthogonal vectors. So Ryan's prominently featured on the slide, so here he is again. He says, in 2005, he said, well, if you believe the strongly exponential time hypothesis, then you better believe that orthogonal vectors require quadratic time, because it turns out that any subquadratic time algorithm for orthogonal vectors can solve SAT faster than 2 to the n time. So this is actually even more believable. It could be that SAT has a faster algorithm than 2 to the n, yet orthogonal vectors doesn't have a faster than quadratic time algorithm. So this one is strictly more believable than Seth.
Are you going to show us a proof?
Yes, at the end of this lecture. At the end of the lecture, I will show you this proof. It's very nice. Now, I mentioned this batch partial match problem, and here I didn't mess up the dimension. So you have a database of n vectors with dimension d, and n queries with some stars. You want to know for every pair every query whether there's something in the database that matches it. This is actually completely equivalent to orthogonal vectors. They're actually the same problem. If you squint, you will see it. So you can think about this being one of the hardness hypothesis problems. Okay. And one more thing, there is this paper that formulates a strengthening of the strong exponential time hypothesis. And now, whether you believe it or not, I don't know. But if you believe it, then it suggests that these three are not equivalent. So in particular, you can't reduce orthogonal vectors to the other two. That's what it shows under some hypothesis. Yeah.
Here by equivalent, do you mean regarding to the specific runtimes we believe are optimal?
Yes.
Okay.
Yes, regarding the specific runtime. They're just runtime.
The hypotheses are equivalent. Yeah.
And
The hypotheses are equivalent.
hypotheses
Yeah,
are
that's all.
equivalent. Hypotheses are equivalent. Yes, with respect to n. Okay. All right, so these are the problems. Now, why these problems? That's, if you have other ideas, go ahead. Yeah.
Is that another one that we use to IPST? Like,
Oh, yeah, you will see. Yeah. Yes, good question. All right. Let's go back to here. So I showed you a few problems we decided to use as hardness hypothesis problems. They come from different areas and different running times. But maybe there's many more. Maybe these hypotheses could be false, but still the theory will still hold because it's about reductions. Okay. So now what I'm going to tell you is the definition of reduction. So first I will remind you what we typically teach in our undergrad courses about polynomial time reductions with respect to NP hardness, and I'll tell you how the new reduction should be different. It will be. So the first thing, what do we usually do, And we teach these many one reductions. What are these many one reductions? We say A and B are some decision problems, so their output are 0 and 1. And we say A is polynomial time many one reducible to B if there's some polynomial algorithm that transforms every instance of A into some instance of B, so that A is a yes instance if and only if B is an instance. In other words, if I have an algorithm that solves B, I can just return the same answer for A. This is what many one reductions do. They have many useful properties that we exploit when we teach hardness, but they have many weaknesses. For example, you cannot reduce a function problem to a decision problem this way, because a decision problem has a one-bit answer. You can't just return. So you have to have many calls instead of one, and this can be fixed by not using a many one reduction, but using a Turing reduction, creating many instances instead. Okay? So that's also something we will do. The other problem is that it's really coarse-grained. So the reduction running time is polynomial, and it can be an arbitrary polynomial, and so the size of B can be an arbitrary polynomial. And so there's no, like, it's too coarse-grained. It doesn't, even if we have like a quadratic time algorithm over here, it could translate to n to the 100 or n to the 1000 over there. It's not useful for our purposes. So we also have to change that. So now I'll give you the definition of fine-grained reduction, which we had in our 2010 paper a while back. So what is the intuition? We have two problems, A and B, and we have running times for them, little a of n, a little b of n. And I want to reduce A to B so that if someone can beat B of n as a running time here, get a better than B of n time algorithm for B, our reduction will give us a better than A of n running time for A. So that's what we want to achieve. So let's do it. Okay, so we say A is AB reducible to B if for every epsilon there's some delta, and an A of n to the 1 minus delta time algorithm that blah, 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 there's a picture. Okay, so what happens here? So we have, for every instance of A of size n, your reduction solves A by running A of n to the 1 minus delta time algorithm, which queries instances of B, okay? Oracle calls. So that if you can solve B instantaneously, then you also solve A by using the answers to B over here, okay? And now we also have this very important inequality that B of n sub I to the 1 minus epsilon, the sum over that is A of n to the 1 minus delta. What does this mean? Okay, we said for every epsilon, there's a delta. For every epsilon, meaning if I had a better than B of n time algorithm, a B of n to the 1 minus epsilon time algorithm for B, then I could apply it over here, right? And the running time of these oracle calls will be the sum of I over B of n sub I to the 1 minus epsilon. That's the running time of the oracle calls. And this inequality says that this is less than A of n to the 1 minus delta, which happens to also be the running time of the reduction. So together, the reduction together with oracle calls with their algorithm applied to them will give me an order A of n to the 1 minus delta time algorithm to solve A. So for every epsilon, there's a delta and a reduction, so that if B is in B of n to the 1 minus epsilon time, then A is in A of n to the 1 minus delta time. Yeah.
Virginia, in the summation above that I need to check in order to check the reduction, what is the range of I? How much do I?
You can have many instances over here. The number of instances can be many.
Can it be more than n?
It depends on your functions. It depends on A and B. Yeah. It can be really big, but it depends on A and B.
So it depends on the algorithm that you're using for.
Yeah. So like if A is like exponential B, and the number of instances could also be exponential, yeah, as long as B is small. So it can be pretty big. The sizes of the instances could also vary. They don't have to be the same. Very. This is the definition. And it has this nice composition property. If A is AB reducible to B and B is BC reducible to C, then A is AC reducible to C. It makes sense. More questions about this?
So the reduction can be adaptive, right?
Oh, absolutely. That's what the oracle calls mean. So I could produce this oracle call depending on what the answer to this one was, you know. Yeah, this could be. They definitely do. Yeah, we really need it to prove some things. All right. So now we have our hardness hypothesis. We have this new notion of reduction, HQ fine-grained reduction with this consequence. Okay. And then we have to actually provide such reductions, and we get a bunch of conditional hardness results. So for NP hardness, originally people got CARP, got 21 NP hard problems, and there's many more that kept added on and on and on. And we would like to be there, but we're not quite there. And you also have problems that are outside of NP, that are NP hard, and so on. But our picture is more like this, okay? So we have these 3 or 4 problems. You can add more problems, but these are the central ones. And you have hypotheses for them. So orthogonal vectors requires basically n squared time, SAT basically 2 to the n, 3 sum n squared, APSP little n cubed, n is the number of nodes, but the input size is n squared, so really it's big N to the 1.5. And we have different things. So let's start with all pairs shortest paths. So in our 2010 paper, we used the notion of reduction and showed that a large number of problems are actually n cubed equivalent to all pairs shortest paths. So that means that a subcubic time algorithm for one of these problems resolves all of them, which is where we want to be. We actually want everything to be equivalent, but we're not there yet. So for example, one thing that Nicole is going to show you in her talk is that this problem, negative triangle, is equivalent to all pairs shortest paths. So let me tell you the problem is, because it's very, very silly. I thought for sure it has a nice algorithm, but it doesn't. Okay, you have a graph with n nodes, and you have weights on the edges. They could be positive or negative, let's say integers. And I want to know if there's a triangle, so 3 nodes, so that the sum of the edge weights is negative. Cubic time is trivial. You just enumerate all the triples of vertices and compute the sum of the weights, but we don't have a better algorithm. And it turns out that if you did, then all of a sudden all pairs shortest paths and all these other problems also have a subcubic time algorithm. So this sort of approach allows you to identify kind of the heart of a problem, the simplest thing that you can think of that will make everything get solved.
This sounds it should be closer to the 3 sum. Is there no connection between the 3?
Great question. So 3 sum is about exact equality. So is there a sum that's exactly 0, where this one's less than? Yeah. But there is a problem that is harder than both, and that's the exact triangle problem, where the sum of weights has to be exactly 0. And I think Ian will mention something about that in his talk. Okay, so for orthogonal vectors, because the problem is so simple, you can show many conditional lower bounds, assuming this hypothesis. And for example, this longest common subsequence problem I mentioned before, you can reduce orthogonal vectors to it in an n squared way, so that if you improve the quadratic time dynamic programming algorithm for longest common subsequence, you can also improve orthogonal vectors and get a faster algorithm for SAT and more. But also many other problems. Nicole will talk a little bit about diameter, the graph diameter, which is related to this problem. For 3 sum, for many years, the computational geometry community looked at 3 sum, and they showed many lower bounds, assuming that 3 sum requires quadratic time. Their reductions weren't fine-grained reductions, but they were pretty good. They were more like many one reductions, so they create one instance. But they still got a huge number of papers out of this and many results. So more recently, we've been able to show that 3 sum reduces to other problems that are not from geometry, like some sequence problems, string problems, and so on. Some sequence alignment problems. And there's many other results. So the number of results keeps growing. There's things about dynamic problems that we'll discuss later and so on. Yeah.
So on Monday we learned that we can find triangles with what's considered homodroid with type n to the 3/2. So why is the problem of finding a negative triangle in Cupid?
Okay, so he says you can find triangles in M to 3. So in M, the number of edges is what the 3/2 is given. And you can do the same for negative triangle. You can also do it in n to the 3/2 in the same algorithm, basically. But the regular triangle can be solved faster than n to the 3/2. So whereas this one, we don't know how to do that. Yeah.
So in general, when we think about the input, we think about the input as the size as. So why does it make sense to think about the input of a graph as the number of vertices?
Good. So he says the size of the input, we usually think about the whole thing, whereas for graphs, sometimes we only talk about n. This is because for graphs, we often talk about dense graphs. So once you fix n, the size of the input is n squared, basically. And the definition I have, you can adapt it for any input measure. It doesn't have to be the size of the input. It could be like some other measure, like the number of nodes and so on.
So what happens? Can you cast all these hypotheses in terms of M, or would things break and then?
Yeah, you can. In fact, I did. Where did I put it here? Somewhere. I don't remember. You can. So right here. This is your N.
Okay, this is okay.
Right there.
And these two things are equivalent.
For this problem, yeah. When your best algorithm is the brute force, often they're equivalent.
I think you wanted to highlight the fact that in the dense graphs we have this nice equivalence. In the sparse case,
that's right. If you in the sparse case, this equivalence. We have different things for sparse graphs.
Totally different.
Because the notion of reductions kind of changes when you change the measure. Like the reduction is the same, but the parameters can change when you do the reduction. Okay, good question. All right. I defined this. So my next goal. Oh, did you have a question? Okay, yeah. So what I'm going to do next is I'm going to give you the reduction from SAT to orthogonal vectors. So you can see that if you believe the strong exponential time hypothesis, then you should believe orthogonal vectors requires quadratic time. Or in other words, if you solve orthogonal vectors faster than quadratic time, then you resolve SAT. Okay. A reminder, what is orthogonal vectors? You have n binary vectors of small dimension, n to the little of 1. Let's say they're S1 up to Sn. Are there two vectors, Si and Sj, so that their inner product is 0? Equivalently, are there two vectors so that in every coordinate C, either Si is 0 in that coordinate or Sj is 0 in that coordinate? That's because they're binary. Okay. There's a brute force algorithm I mentioned, n squared, which is n to the 2 plus little of 1 because the dimension is small. And the best known algorithm is this. And we'll show this theorem over here. If OV had an n to the 2 minus epsilon time algorithm for any epsilon that you pick, then set is false. Set, again, for every epsilon, there's a case, or the case sat on n variables and m clauses cannot be solved in 2 to the 1 minus epsilon times n time. In other words, if you had a better than 2 to the n time algorithm, for some epsilon that can solve SAT for all k SAT for all k, then SAT is false. So we need the same epsilon to work for all the k's. And this is a theorem. Let's start. Let F be your formula on n variables and m clauses in CNF form. For example, this one. OV, there's a set of n vectors. Big N will be the number of vectors, and little n is the number of variables, okay? And n vectors in small dimension, you want to know if two are orthogonal. What we want to do is, given this formula, we want to create a set of vectors in small dimension so that there is an orthogonal pair if and only if f is satisfiable, and we want the number of vectors to be roughly 2 to the n over 2, and the dimension small. So if you have the number of vectors to be roughly 2 to the n over 2 and small dimension, then a subquadratic time algorithm in this will be a less than 2 to the n algorithm for SAP. So we'll use this nice approach that takes the variables and splits them into 2 halves of n over 2 each. And now this 2 to the n over 2 part over here should give you an idea what to do with these n over 2 things. We have to enumerate something. Okay, so what do? We'll, for v1, let v1 be the first part of the variables and v2 the second part. We're going to enumerate all partial assignments to the variables in v1 and all partial assignments to the variables of v2. Okay, so there are 2 to the n over 2 for each of them.
This is any partition?
Arbitrary. I don't know how to do better with a special partition, but you arbitrarily split them. Okay, so for example, if I pick v1, here v1 is x1 and x2, the first 2 variables. I look at the partial assignments. X1 is set to 0, x2 is set to 0, x1 is 0, x2 is 1, and so on. There's 4 of them. All right. Now, for every choice of v1 or v2 and every partial assignment phi for vj, we will create a vector whose length is the number of clauses m plus 2. And let's call this vector v of j and phi. Phi is the partial assignment, j is the choice of 1 and 2, which picks whether you're taking the first half or the second half of the variables. Here's how we'll pick it. So for v1, the first 2 coordinates will be 0, 1. And then you have a coordinate for every clause. Okay? And what do you put there? So remember, we have a fixed partial assignments to v1. And we're going to look at each clause, let's say this one, and we're going to put a 0 if that partial assignment satisfies the clause. And we'll put a 1 if it does not satisfy the clause. We do the same for the second half of the variables, except over here, instead of 0, 0, 1, we put 1, 0. So again, we check, does this satisfy this clause? Is the partial assignment satisfied? And we put a 0 if it does and 1 if it doesn't. So here's an example, right? We have this formula over here. v1 is this, and v2 is the second half x3. And let's say we want to form the vector corresponding to the first half of the variables x1 and x2 for the partial assignment where x1 and x2 are set to 0. The first 2 coordinates are 0, 1 because we're talking about the first half of the variables. And then we look at each clause. For the first clause, we check, does the partial assignment 0, 0 satisfy the clause? No. So we put a 1. Does the partial assignment 0 to x1 and 0 to x2 satisfy this clause? Yes, because not x1 is 1, so this one's satisfied. So then I put a 0 here because it's satisfied. And in the final one, x1 and x2 do not appear at all. Okay? So there, no matter what assignment I pick for them, this will not be satisfied. So I'll put a 1. Okay? This is clear. And very easy to construct these vectors. Just to the n over 2 time. All right? There you go. So the first thing is that if I have 2 vectors that correspond to the same half of the variables, let's say to v1, then their inner product will not be 0 because they both have a 1 in this coordinate. If they're in the second, if they correspond to the second half of the variables, they both have a 1 in the first coordinate. So again, they're not orthogonal. So the only possible way they're orthogonal is if one is for v1 and the other one is for v2. Now, we look at every clause. Orthogonality means that for every clause, at least one of them is 0. Okay? But at least one of them being 0 means that at least one of phi or psi satisfies the clause. So 2 v1 phi and v2 phi are orthogonal if and only if together phi and psi form a satisfying assignment. So because for every clause, at least one of them satisfies. So the set of vectors we created has an orthogonal pair if and only if the SAT formula is satisfiable. The number of vectors is 2 times 2 to the little n over 2. And the dimension is the number of clauses plus 2. And this is an OV instance. So if you had, for example, an n to the 2 minus delta times poly d time algorithm for orthogonal vectors on d dimensions and n vectors, you would get a 2 to the little n times 1 minus delta over 2 poly m time algorithm for SAT. Okay. And then SAT will be. Okay. Yeah.
In this particular case, this is a many one reduction, right?
Yes, this is a many one reduction. You will see a real fine-grained reduction in the next lecture, I believe.
So there is nothing to be gained by the fact that it's a many one reduction. I mean, it's not nicer because it's. No.
I mean, it's very clean. It fits on the slide, right? But yeah, and some things you can prove some things with many one reduction, but many of the things you'll see you won't be able to. Okay.
Does it make sense to look at the other direction of the integration as well? Like if you have a slope of v, then that implies that set is true.
Oh, you want to say, can we reduce SAT to orthogonal vectors to SAT?
Yes.
I've tried and it failed. But there, you need to have a menu. You can't do it with a many one reduction. So you would need some sort of full fine-grained reduction where you create a ton of little instances, so that like a 2 to the n over 2 or 2 to the 0.99 algorithm on them will be still fast enough to be quadratic, right? So the little n that you get there has to be very tiny somehow. But I just couldn't do it. I think maybe you tried too. Maybe you can do some things.
It can't just be like an arbitrary set of vectors. Yeah. There needs to be something, it needs to be compressible, similar to how like CNF is a representation of the whole PDN space.
Yeah. But like in the full generality, you can't. I don't know how to do it. It might also not be possible. Maybe OV is just harder. You know? I don't know. Yeah, so I think actually I'm a little fast today, because I'm gonna finish early. But if you have any questions, please. Thank you.
I was wondering, do you know if your framework is easily extendable to the case where you have an additional external data structure that allows you to serve as an oracle or something like that? I'm thinking like, what if you have an index in a database or something like that?
Maybe I don't understand quite. So like in both problems you have a database, or?
Well, in the beginning of the talk, you talked about we have these problems with these upper bounds, and we don't know how to improve them.
Yeah.
Now, of course, if for some of these problems, if you already have something in place, which is on your data, and then you get query or whatever, then you can answer some of these problems more efficiently, right? For example, if you have a two-hop index or something like that in place, and your query asks about reachability of two nodes, you just have to do one join instead of doing a whole path or something like that.
Yeah.
Have you thought about settings like this?
I mean, I guess in a sense, when we give the lecture on dynamic algorithms, that's about data structures. But it's not, what I'll talk about won't be between like two problems that both have data structures. I'll show you how you can reduce one of these to some data structure type problems. But yeah, that's also a good question. I do think the framework does extend. You have to be more careful, but I think it does.
Just a conceptual question. So this fine-grained complexity, as far as I understand, is based on identifying some problems and looking at all problems that are reducible to them via these reductions. So the classes that arise from this are based on one problem as opposed to having them defined via some other resources. has this been tried? I had talked to Amir Abud when he was at Almaden a little bit about this, and the question was whether we can have a descriptive complexity or fine-grained complexity. I think you've done a little bit work on that.
Yeah, they had a very nice paper, Ryan and others.
What is the summary of it? Does it make sense? And how far have you gone?
With some first order logic definable problems, right? Do you want to say something? Yeah. Yeah, you can define various problems using first order logic, and you can prove some completeness, like OV is complete for this class or something like this. And yeah, do you want to say some more?
Oh, no, yeah, I mean, I can point you to some references to,
Maybe someone should
Well,
give a talk.
you take some fragment of first order logic and you say model checking on this, like how complicated is it?
Yeah.
Just on the logic of graphs or something. You could say what is the hardest query problem to solve here and how fast they are. I had some paper about the dense case, and then Antonina and Russell and Zhao and Gao, we had a paper on the sparse case.
But some of these problems
Beyond
don't fit
that,
there.
They don't fit.
I haven't even kept up with all the work.
I think what you guys did was like related to OV and like triangle stuff and things like this, but threesome, for example, didn't fit. So like, there's a lot of these problems don't
So you would
fit.
want to take some number theoretic logic or something, right?
Yeah.
To talk about threesome, I guess that would be interesting.
Yeah, it would be nice to have it all fit, but not all. Some of them you can describe a lot of things, but not all so far. Yeah, but we should have a talk about this.
Can you prove anything about matrix multiplication under fine-grained hardness?
So matrix multiplication. Well, matrix multiplication, we can prove some equivalences to matrix multiplication under some notions. But maybe matrix multiplication isn't quadratic time. So I mean, there will be linear time in the size of the input, and then I don't know. But assuming it is not, you can show a bunch of relationships to other problems. Yeah, and of course over single rings, you can show stuff.
So do we have any reason to believe or not believe that we can have reductions between these basic hypotheses to connect them somehow? Because right now they are kind of independent hypotheses, right? And there are other hypotheses as well that are introduced. So
we're actively working on trying to connect them. We're always actively working. We have problems you can reduce all three of them to. We have problems you can reduce two of them to, but not the third and the second, like assuming some conjectures. We're trying. And under some assumptions you can do things. Anyway, I guess we have to give yet another talk on this, and we didn't have time for this. Yeah.
How do you pick the computational model? Is there any practical implication of it?
We just pick the one that people usually study in algorithms. But again, you can change it. Then you have to be careful that your reduction can run at the appropriate time in that model. Yeah, it's a good question.
So you mentioned that you cannot, or you don't know how to reduce the orthogonal vector problem to set. Right? Are there any natural problems that can be used to set? Evidence that this is?
I mean, there's some papers that give equivalences between various other problems in exponential time to set. Yeah.
But it's problems that can be solved in exponential time.
Yeah.
But like polynomial time, like reduction from polynomial time problem.
I mean, I think we can probably do that. I don't think anyone's published anything, but it won't be natural. Yeah.
No, just to provide evidence in the sense that, I don't know, threesome actually somehow, I mean, we believe that cannot be done in time less than n squared.
Yeah, I'm not sure how to do it. Oh, maybe this program we can do it. Yeah.
Any other question? No? If not, please come back in 30 minutes.